Hi, my name is Raphaela de Oliveira and I'm a PhD student of the Physics Department of the Federal University of Minas Gerais. I will present my most recent work with Stanislav Balabanov and my supervisor Klaus Krambrock on the establishment of conditions to improve the luminescence properties of zinc selenide for its application as a scintillating bolometer in the search for the neutrinoless double beta decay. The neutrinoless double beta decay is expected to occur for just a few isotopes and is described by the transmutation of 2 neutrons into 2 protons emitting 2 electrons, beta particles, but conserving charge but without emitting neutrinos. This rare event is predicting extensions of the standard model and carries important information about the nature of neutrinos and their mass scale. This event is only possible if neutrinos are Majorana fermions, violating the conservation of the lepton number during the decay. The efforts to develop experiments capable of observing the neutrinoless double beta decay are justified by the huge relevance that its detection would have in the field of particle physics, opening new doors for research beyond the standard model. Cupid is one of the few experiments in the world developed to detect the neutrinoless double beta decay, based on scintillating bolometric technique using zinc selenide crystals enriched with the Ag2 selenium isotope, an isotope predicted to decay by this process, as the core of individual detector modules. The modules are arranged in a tower-like structure, where each module consists of a luminescent cylindrical zinc selenide crystal coupled to thermistors and a thin film of germanium deposited on its surface for light detection. The entire system is kept refrigerated at controlled cryogenic temperature of the order of millikelvins. The scintillating bolometric technique is capable of reading simultaneously a heat and a light pulse, producing the material due to an interaction with a particle or radiation. So how it works? The core of a scintillating bolometer is made of a material with good thermal conductivity and good scintillating luminescence properties, where the particle interaction will occur. In your case, this material is a zinc selenide crystal enriched with the selenium isotope. Coupled to this material, we have thermistors for measuring the thermal variation of the material, and a light signal, a light detector for measuring the light signal. If selenium isotope decay, will be released an amount of energy that will rise the temperature of the material, and this thermal pulse will be detected by the thermistors. Also, as the zinc selenide is a scintillating luminescent material, part of the released energy of the decay will be converted into a light signal that will be detected by the light detector. This combined result allows to effectively discriminate different types of particles due to different luminous fields that each interaction induces in the material, leading to a drastic reduction to the detection background level of the experiment. For this reason, the improvement of luminescence properties of zinc selenide is the key to reduce even more the detection background for its application as a scintillating bolometer in experiments that search for neutrinoless double beta decay. The zinc selenide is a 2,6 semiconductor with a direct band gap of 2.7 electrovolts and grows in a face-centered cubic structure. In a previous work, we investigated luminescent zinc selenide crystals enriched with the selenium isotope grown by Bridgman technique. By PR measurements, we observed the presence of some impurities and very low concentrations, and we identified by photo-EPR zinc vacancies paired with shallow substitutional impurity donors of aluminium as the dominant radioactive recombination center responsible for the yellowish-red luminescence typical of the zinc selenide. The literature explores several types of A centers that can be responsible for luminescence bands in the yellow to red X-spectral region. However, the conditions under which the material becomes luminescent and the process that leads to it has not been established yet. In this work, we investigated 3 types of ultra-pure polycrystalline non-luminescent samples of zinc selenide grown by CVD method by the Stanislav group of the Russian Academy of Science. One type of the samples was grown as stoichiometric, named ZnSe, and the other 2 types were grown with excess of selenium or zinc in the composition of the samples, named as ZnSe-Se and ZnSe-Zn. We submitted this mother group sample to several processes: thermal treatments, gamma and particle radiation, and doping process with aluminum and gallium by diffusion and ion implantation to obtain efficient luminescent samples and establish the process capable of improve the luminescence properties of the material for its application as a good scintillating bolometer. On the mother samples group, EPR measurements were performed in the temperature range from 5 to 300 Kelvin under UV laser excitation and in the dark. However, no spin resonance transitions were observed for different samples orientations and different parameter settings. The non-observation of EPR signal was not unexpected for the ZnSe mother sample, considered stoichiometric and ultra-pure by the growth group. But for the selenium-rich sample and the zinc-rich sample, it was expected to observe EPR signals of intrinsic defects such as vacancies or interstitials. The non-observation of EPR signal may indicate that the point defects exist in concentrations below the detection limit, about ppm in some cases, or they mean in non-paramagnetic states. Another characteristic of the samples that could contribute to the non-observation of EPR signal is the polycrystallinity. If the samples were formed by microcrystals of the order of hundreds of micrometers, the distribution of the resonant transitions along the magnetic field for each microcrystal oriented in a different way reduces the EPR lines, the intensity of EPR lines, and they may not be distinguishable from the measurement noise. Gamma image spectroscopy was performed to investigate the polycrystalline character of the samples. Interpreting the image contrast as a different oriented microcrystal, we can estimate grains with dimensions of the order of hundreds of micrometers only for the ZnSe sample. So the polycrystalline character of the samples could justify the non-observation of EPR signals just for the zinc-rich sample, while the other two mother samples should have an EPR spectrum closer to a powder spectrum due to the estimated size of their grains. Quantitative microanalyses were performed by wavelength dispersive spectroscopy, and impurities were not observed, confirming the ultra-high purity of the samples. But comparing the mother samples with an ideal zinc selenide stoichiometric crystal, the quantification shows that there are no significant stoichiometric difference between the samples within the uncertainty of the measurements. The high purity and low deviation from the stoichiometry of the samples are a characteristic of the CVD growth method, even with a significant excess of one of the components during the growth. And this can be the reason for the non-observation of EPR signals. The absorbance measurements of the model samples corroborate the fact that there was no evidence of the existence of intrinsic or extrinsic defects since absorbance bands were not observed within the band gap of the zinc selenide. The only difference between the spectra of each sample is the behavior close to the optical gap of the material at approximately 2.65 electrovolts. This behavior can explain the different colors of the samples, which may be related to the formation of selenium clusters during the growth. The absorbance measurements show that the ZnSe SE sample has an enhanced absorbance in the blue to green spectral region, giving it a more orange color, while the sample ZnSe Zn has less absorbance at these wavelengths, giving it a more greenish color. The ZnSe sample of intermediate color between the two others also has an intermediate behavior for the increased absorbance close to the optical gap of the material. The mother samples are non-luminescent, so they did not show noticeable luminescence to the naked eye under UV laser excitation at room temperature. Also, the PL spectra of the samples at room temperature did not show any bands, as expected. But as the temperature decreased, some PL bands became visible. In the low temperature PL spectra of the mother samples measured at 20 Kelvin, it's possible to identify acetonic peaks and two broad luminescence bands. The PR spectra of the also endorse the fact that the samples are very poor, since no luminescence bands is detectable at room temperature, and acetonic peaks are observed with the decrease of temperature, common features in ultra-pure samples. However, the broad luminescence band, centered at 575 nanometers, lies in a spectral region characteristic of the defect-related PL bands in zinc selenide, originated from the radiative recombination between A centers. The existence of these PL bands suggests that the defects or impurities are present in the samples, but in very low concentrations, since we cannot observe it by other techniques. In addition, the luminescence band, observed at approximately 715 nanometers, endorses the suspicion that defects are present in the samples, even at low concentrations, since this band corresponds to the luminescence associated with the isolated zinc vacuums. The gamma-irradiated batch of samples was prepared from each mother sample and submitted to a 200 kg dose of gamma radiation in order to ionize possible existing defects in the mother samples and increase the concentration of the paramagnetic centers. However, no spin resonance transitions were observed. Still trying to ionize some point defects, an electron-irradiated bath of samples was also prepared for each mother sample and submitted to particle irradiation with rapid electrons up to a dose of 30 megagrade. The only PR signal observed was an isotropic line close to the defector for the free electron, caused by a Zeeman interaction of a half spin without modification under UV laser excitation. The signal is too generic to conclude its origin. None of the most common defects in zinc selenide, such as isolated zinc vacancies or complexed zinc vacancies, have the characteristics of the line observed in the samples. One hypothesis for the origin of the signal is that they could be related to a simple shallow donor, but the levels for shallow donors in zinc selenide are too close to conduction band, making it difficult to observe by EPR due to a limitation of the technique. On the other hand, to give mobility to the sands and allowing them to complex in new ways, thermally treated batch of samples was prepared from ZnSe mother sample and submitted to the heat treatments performed at 200, 400, and 600 Celsius degrees for 1 hour in inert atmosphere. It was expected that the concentration of paramagnetic centers would increase with formation of complex defects such as A centers. But the same EPR signal observed in the electron-irradiated samples was observed for the thermally treated sample. The no observation of typical EPR signals for zinc selenide after this process confirmed that the defects present in the mother samples exist in very low concentrations, below the sensitivity of EPR technique. Also, it is important to note that the samples remain non-luminescent under UV laser excitation at room temperature after all this process. So in order to improve the luminescence properties of zinc selenide, it's time to try to insert some impurities on the samples. Two samples prepared from the ZnSe mother sample were doped with aluminum and gallium separately by diffusion method in a muffle furnace at 600 Celsius degrees for 100 hours in vacuum-sealed quartz ampoules. And finally, we got luminescent samples. The aluminum doped sample showed a strong luminescence under UV laser excitation, and the gallium doped sample showed a less intense luminescence. From the PR measurements as a function of temperature for the aluminum doped sample, it's possible to identify only a broad luminescence band, centered at 597 nanometers, that increase in intensity with the decrease of temperature. This band has already been associated in the literature as a result of high doping by diffusion with aluminum in zinc selenide. It is also related to radiative recombinations of complex defects involving zinc vacancies as acceptors and donor states introduced by the aluminum impurity. For the PR measurements for the gallium doped sample, we can observe the presence of several extonic peaks and two broad luminescence bands, The PR band observed at 540 nanometers has already been reported in the literature as the recombination of A centers in gallium-doped zinc selenide crystals. The new band observed at 635 nanometers may also originate from radiative recombinations of other configurations of complex defects involve donor states introduced by the gallium impurity and the zinc vacancies as acceptors. Comparing the luminescence of the diffusion doped samples with the mother sample ZnSe, we can observe that the stonic peaks of the mother sample are also present in the gallium doped sample, in addition to new peaks, but suppressed in aluminum doped sample. This result indicates that the diffusion doping method was more effective for the aluminum doped sample, in agreement with the fact that the sample showed a more intense luminescence than the gallium doped sample. X-ray photoelectron spectroscopy measurements were performed to confirm the effectiveness of the diffusion doping process. The spectra of the aluminum doped sample was acquired after successive sputterings to clean the sample surface, but it was not possible to identify the presence of aluminum in the material. The non-observation of aluminum on the surface of the sample may indicate that the doping process was more effective, since it's probable that the aluminum had penetrated more into the material during the diffusion process than the gallium, concentrating the bulk of the sample, and the aluminium atoms that remain on the sample surface may have been removed during the sputtering process needed. On the other hand, the spectra acquired for the gallium-doped sample detected the presence of gallium after only one sputtering process. This indicates that the diffusion doping process was less effective in comparison with the aluminum doped sample, concentrating gallium more on the surface than on bulk. And this is consistent with the fact that the sample shows a not so strong luminescence. The Gaussian fit performed on the peaks related to the 2p orbital of the gallium indicates that the gallium atoms are partially bounded to oxygen atoms, naturally oxidized on the sample surface, and partially bounded to selenium atoms, since they enter as a substitutional donors to zinc in the material, as we expected. EPR measurements were also performed, but no spin resonant transitions were observed. It was expected that the luminescence-doped samples would present EPR signal related to the A centers, since the characteristic luminescence in the yellowish-red spectrum region of the zinc selenide is associated with the paramagnetic states of complex defects, and they will be present in significant concentration in the luminescent samples. However, the no observation of EPR signal, even in luminescent samples, may suggest that the luminescence of the material can be originating from the radiative recombination involving the non-paramagnetic states of these defects. In parallel with the diffusion doping process, one of each mother sample was submitted to doping with gallium and aluminum by ion implantation. The ion-implanted samples just become luminescent after heat treatment, performed at 400 Celsius degrees during 1 hour. This is because during the implantation process, the atoms penetrate the material in arbitrary positions, destroying the lattice. So it's necessary to perform a heat treatment to restore locally the lattice and increase the mobility of the vacancies and impurities to allow the complexation of defects which the yellow-red luminescence characteristic of zinc selenide is associated to. EPR measurements were also performed, but no spin-resonant transitions were observed. In the PR measurements on the ion-implanted sample doped with gallium, it is possible to identify two luminescence bands by the Gaussian fit of the PR spectrum measured at 20 Kelvin. The band centered at approximately 623 nanometers is also present in the diffusion gallium-doped sample. So we can associate directly this PL band with radiative recombination of complex defects involving a shallow donor state due to the gallium impurity. The luminescence band observed at 672 nanometers was not resolved for the diffusion gallium-doped sample, but it also can be associated with complex defects involving gallium impurity. In the PR measurements for the ZnSe SC model sample implanted with aluminum, it's possible to identify two bands with the Gaussian fit of the PL spectrum measured at 20 Kelvin. While for the ZnSe SC model sample, also implanted with aluminum, it's possible to identify only a broad luminescence band dominant in the spectrum. Comparing the PL spectra of the diffusion aluminum doped sample with the two samples doped with aluminum by ion implantation, we observe that the bands are not completely equivalent. However, it's possible that the bands observed in aluminum ion implanted samples were also present in the diffusion aluminum doped samples, since the dominant band of the PL spectrum for the diffusion doped sample with aluminum is broadened and unresolved to the red. The observation of extonic peaks in the ion-implanted samples confirms the effectiveness of the doping, since the luminescence contributions of the model samples were suppressed. As a result, this work demonstrates that only processes that introduce donor impurities into the material are capable to strongly improve the luminescence properties of zinc selenide. The implication of this result is that the complex defects involve donor impurities, and zinc vacancies, A centers, are the most efficient centers of radiative recombination in the material. This work also indicates that the introduction of impurities in low concentrations is already sufficient to make the material notably luminescent. Thus, the needed introduction of impurities to increase the luminescence of the material may not compromise its application as a scintillating bolometer, since the low detection background archived in the hair events experiment can be easily maintained by correction once the impurity and the concentration is known. Finally, these works indicate the ultra-pure growth of zinc selenide by the CVD method with controlled and homogeneous insertion of doping impurities, aluminum for example, during the growth process as a successful methodology to produce zinc selenide crystals with good luminescence desired for its application as a scintillating bolometer. So that's it. Thank you everyone.